Okay, hello, welcome everyone to the day 3 of the Kumquat Conference. We're starting now the presentation session of the theoretical physics, and our first speaker will be Jakub Jerzowski, and he will give us a talk about the fluorescence, pure physics in aid to biological sciences. If you're ready, you can share your screen and carry on.
Okay, hello everyone. First thing, do you hear me well?
Yes.
That's perfect. So let's see. So can you see my presentation?
Yes, but it's not yet in the presentation.
No.
Yeah.
Okay, so I think that we are ready. So once again, hello everyone. I'm Jakub Jerzowski and I am a student at the Faculty of Biochemistry, Biophysics and Biotechnology at the Jagiellonia University. And today I will tell you a little bit about the fluorescence and its application in biological sciences. Let's start with the plan of my presentation. First, the introduction about the fluorescence. I will tell you a little bit about it. Then basic laws of the fluorescence. And at the end, I will present you my own results from my research, as well as some interesting facts. So let's start with luminescence. What is the definition of luminescence? Luminescence is an emission of light from an object which is not a result of heating up this object. Then what is the definition of the fluorescence? The common definition would be the same for the luminescence and for the fluorescence. But for the scientific one, we have to go into more details. There is a third phenomenon, phosphorescence as well, but I will tell you about it a little bit later. So one of many definitions of fluorescence. It's emission of light, which is incidental to returning of an electron from singlet excited state to singlet ground state orbital. Those two words, singlet, are very important because the only difference between the fluorescence and phosphorescence lays here. In phosphorescence, electron returns from states of different multiplicity, and therefore it's much slower. In fluorescence, the multiplicity is the same. It's usually the singlet state orbital and transition between those two. The very next slide represents Jabloński diagram. And Jabloński diagram is a very elegant representation of processes which can occur upon the absorption of a quantum of light by a molecule. First, let's look at the features of this diagram. Let's start with the orbital states. Here is an orbital state, here is an orbital state, as well as here and here. It represents the energy of the molecule, and the energy of the molecule may be further quantized into vibrational states. And you can see them here as well as here and here. So upon the absorption of light, which is very, very quick, the molecule may go to excited electron state or excited vibrational states. After that, something called internal conversion and vibrational relaxation occur. Those processes are coupled and they usually occur together, and they are very, very quick, much quicker than fluorescence usually. So they happen prior to the fluorescence. And this is the reason why the molecule usually returns from the ground vibrational state, but excited electron state to the ground electron state in the process of the fluorescence. Additionally, there is one process, the phosphorescence I mentioned, but it occurs very rarely because it needs intersystem crossing, and intersystem crossing is a forbidden transition, so it happens very rarely, as well as the phosphorescence is very, very slow. It may take seconds, minutes, and even hours for the phosphorescence to occur. Now let's talk about laws of fluorescence. Stokes shift. There is a difference between peak of emission spectrum and peak of excitation spectrum. Here is a graphic that will illustrate it to you. So here is the peak of emission spectrum, and here is the peak of the excitation spectrum. And as you can see, there is a difference in the wavelength between those two. This difference may be quite large, like here, or quite small, like here. It depends on the specific fluorophore. And what is a fluorophore, I will tell you in a moment. I may add that this observation is very practical because it helps us to distinguish fluorescence, the light from our sample, it's here, and the light from our source. So this is the wavelength that is emitted. This is the light with the wavelength emitted by our source, and this is the light emitted by our sample, by a fluorophore. Now, let's go to the Cashas rule. So, general shape of emission spectrum is always indifferent. That is, shape of emission spectrum does not depend on excitation wavelength. That is, whether you use this wavelength to excite or this wavelength to excite, you will get generally the same spectrum. If we use this one, we'll get something like this. And if we use this one, we'll get something like this. As you can see, general shape is the same. The only difference is in the intensity of this fluorescence. This is second very practical observation because now we can choose different wavelengths to excite our fluorophore, and we can get very same results. And only the intensity of the fluorescence probably will change. Now let's go to the application of fluorescence and what is a fluorophore. So YY1 is a protein that influences genes expression which regulate different cellular processes. You can see it here. It's a crystal structure of the YY1. It's an actual structure that was obtained through X-ray diffraction. And here is the DNA molecule which is bound to the protein. Here is what is a fluorophore. Fluorophore is a fluorescent chemical compound that can remit light upon light excitation. We can distinguish synthetic and natural fluorophores, and some amino acids like tryptophan are natural fluorophores. Now, let's take a look at the graphic I prepared for you to illustrate my research. But first thing is most important. What are the questions that I wanted to answer? Can fluorescent signal show whether two molecules interact, and can it help to distinguish different interaction between those molecules? As you can see, this blue or violet object is my protein, and there is an inherent natural fluorophore in it. Here we have the DNA sequence, and here we have the different DNA sequence. Those two molecules are mostly the same, but there is a slight difference in them. Proteins are the same. So we mix it together in a tube, then we put it to the cuvette. Here's a source of light that excites our fluorophores, and then we detect the the signal, the fluorescence signal from our cuvette. And as you can see, this protein interacts differently, in theory, of course, differently with this sequence and with this sequence. It's more horizontal is more vertical. And in theory, there should be a change in the fluorescence signal because of these differences in the interaction. As you can see here, the intensity changes. Okay, that's the theory, but what are the actual results? Here you can see a graph I prepared for you. Here is our protein, ZF1. I called it because it's got additional mutation. Tryptophan, as I mentioned, is a natural fluorophore and it's mutated into this protein. And here you have the basic intensity of the fluorescence from the protein. And as you can see, when we add DNA, those are different DNA sequences, the intensity decreases. Here we have a second example. It's almost the same protein, but the only difference is it's got arginine residue in it as well. And arginine residue, it's an amino acid which may help to facilitate the contact between protein and DNA. So it may help in the interaction. And now you can see that the intensity of the fluorescence increased in most of the cases, in all cases with in the DNA. So to sum this up, we see the decrease in the fluorescence signal and increase in the fluorescence signal depending on only one residue, only one amino acid in the sequence of the protein, which contains hundreds of amino acids. And you may ask, what is the reason for that? Why do we do that, actually? First of all, just out of the curiosity, because we are curious, and I think it's one of the most important reasons. It helps us understand the cellular, how our cells work, how it all interacts with each other. And the second reason would be drug design, new therapies, and other biotechnological inventions. And we can do that because we understand the process, understand how the protein and the DNA react with each other. And that would be it from me. I thank you very much for your attention. Here are the sources I used, as well as the articles and books. And as I've mentioned, results presented are from my own research. So thank you very much again. And I think it's a good time for some questions, if you have any.
Yes, thank you very much. I don't see any questions on the stream chats, but maybe some participants here on the Zoom want to ask us something. If not, then I have a question of my own. So first of all, are you aware of what kind of experimental setup is used for this fluorescence detection? Because as I understand, it is very low in intensity, like relatively to.
Yes, it's very low, and it's it's an excellent question actually, because usually setup is very complicated and it's very expensive. And as you've mentioned, the intensity is very low, and we can detect as low as, I would say, 100 or from 100 to 1000 quantums of light at once from the fluorescence signal. So there are spectrometers, spectrofluorometers actually, and there are different spectrofluorometers, but they are very expensive and very different, I would say. So there may be different setups for this.
Okay, so thank you very much then for your presentation. And now we will move on to the next speaker. Thank you. And now we have Negin Khosrovanineza from about cosmic web in large-scale cosmology simulations. So, are you with us?
Hello.
Yes, hello.
Can you give me a moment to share my screen? May take like
yes, okay.
10 seconds.
Okay.
Okay, I'm so sorry for the inconvenience. Can you see my screen now?
Yes, yes.
Okay. Okay, so start video. Okay. Hello, everyone. This is Negin Khosrovanineza. I'm an undergrad at Sharif University of Technology, and today I'm going to talk about my project in our Cosmic Web Research Group. Okay. The technical aspect of what I'm going to talk about might be kind of complicated, so I have to start with a relatively long introduction. Let's begin from what cosmology is. As the Cambridge Dictionary suggests, cosmology is the study of the nature and origins of the universe. According to this definition, for example, Ptolemy, who used the available data at his time to develop his geocentric model, or for example, Copernicus, who developed his heliocentric model, should be considered as cosmologists. But actually, that is not the case. Today, we call by cosmology, we mean the set of studies and observations done after the works of Mr. Edwin Hubble. When Hubble came, it had been more than a century that people knew what spectral absorption lines are supposed to be observed from the sun or any other star. They were acquainted with the Fraunhofer optical lines like calcium, magnesium, or the ultraviolet lines like helium, hydrogen, etc. In addition, they knew about the redshift effect. That is when an emitting source is moving away from us, we see a shift, we see an increase in the wavelength of the spectral line. Having those in mind, what happened in 1929 was that Hubble looked at some galaxies whose distances were already measured by some other method. And then he saw some redshift in the spectral lines of those galaxies, meaning that they are moving away from us. And Hubble also found a correlation between the redshift and the distance to those galaxies. And this is for all the galaxies. This simple discovery became the basis of the cosmology in the whole century. And even today, how we study the universe is based on the same thing. Actually, we look at the sky, we see galaxies with different redshifts, and having the Hubble relation, we know that these different redshifts determine different distances. Combining this simple idea with the physical fact that the speed of light is limited and is a constant, we can say that by looking at different redshifts, we are actually looking at different times in the past. Because the further a galaxy is from us, the more time it takes for its light to reach our eye. So we expect to look at the sky and see the history of the universe from the beginning until now. But unfortunately, that is not the case. Because at the very beginning time, the universe was so hot and so dense that the photons were like stuck among these fast electrons and protons, and they couldn't escape to reach our eye today. But there was a special time at the redshift of 1100 when the reionization of electrons and protons happened, and since that time, light can emit and can travel through the universe. Now, when we look at that time in the past, we see anisotropic black body radiation that is called the cosmic microwave background, or CMB. For decades, cosmology was all about looking at CMB and finding the parameters of cosmic models. By looking at CMB, I mean measuring the anisotropies of its temperature at different angular scales and drawing its spectrum. So this is what cosmologists do. They determine cosmic parameters by looking at the power spectrum of the CMB. You might have seen this photo. This is the photo of the universe at different times. This is the special time that I was talking about. It's where the CMB radiation is coming from. But as you see, there are many other times in which many other things happened in the universe. And there must be more information in them in comparison to only the CMB. And that is why cosmologists are interested in large-scale structure, or LSS. Unlike the CMB, the LSS is not only one snapshot, it's a motion picture during the time. And unlike the CMB that belongs to a region in which gravity hadn't still played a big role and the structures were linear, large-scale structure contains non-linear structures. And that is why we think that instead of the only 6 parameters of lambda CDM, which is the standard model of cosmology, in addition to them, we want to take out more parameters from the LSS. When you look at the large scale structure of the universe, you see that every here and there are some voids, like empty regions, like this one and this one. And between these voids are filaments of matter and dark matter. And this is why cosmologists call this the cosmic web, because it looks like a web. And what I'm going to do now is talk about the simulation of the cosmic web. What people do to simulate it is they put matter in a box. The matter has a uniform distribution and it has some small initial fluctuations in it. Then they apply an n-body simulation working with gravity, means working with general relativity. And as time passes, the gravity plays its role and the small fluctuations change into filaments with voids between them. And this is the larger structure of the universe. And as you can see in the later stages, which are the recent years, the LSS hasn't changed that much in the last row. The LSS hasn't changed that much because the region when matter was dominant in the universe, which means the gravity played a big role in the universe, is over. And another region has begun, which in this region, something else, dark energy, is dominant, which doesn't relate that much to our discussion here. What we want from these simulations is to find a way to measure our cosmic models, because we know that the lambda CDM model cannot explain well many phenomena today. For example, there is an assumption that comes from the standard model of particle physics that says neutrinos are massless. And from this assumption, the lambda CDM model does not assume a parameter for neutrino mass, for the total neutrino mass of the universe. But we know that there is also another theory that is the solution to the solar neutrino problem that suggests that neutrinos do have masses. And the three types of neutrinos oscillate into each other because of the differences in their masses. So we want to use the cosmic web simulation to decide which of the theories work better. And we do this by using the simulation and comparing the results of the simulation with the observation from the real universe. For example, we run one simulation with assuming that the total neutrino mass of the universe is 0, like the lambda CDM model assumes this. And we plot the power spectrum of matter, which is the anisotropies of matter, or it's better to say the contrast in matter, as a function of a scale. Okay, so we plot this power spectrum for neutrinos with 0 mass. We do that again and plot this for neutrinos having mass. We can do this for different masses by assuming different masses of neutrino. And what we do here is to compare the results of the simulations with the observation from SDSS or any other satellite that gives us this information, and then decide which of the model are better. Of course, what we do is not using this exact plot. We use this plot, which is the same as the previous one, but is the ratio of each power spectrum with assumption of these masses for neutrino to the lambda CDM, the zero mass neutrino power spectrum. And we can use this plot if we have the plot of power spectrum that we take from observation. We can determine which theory works better, and we can determine a mass for the total neutrino of the world, and even solve a problem in the standard model of particles. Okay, this was our project. I can hear your questions.
Thank you very much. Are there any questions from the participants here or from the jury?
I have a question, if I may ask.
Great, go ahead.
So, as far as you told us, you have been, I'm not sure if you have been doing those calculations of n-body systems. So in general, if you have a many-body system and they all interact with each other, it is a very difficult problem to solve. So how many actually bodies did you include in your calculations, and what kind of approximations did you have to do to be able to get the solution in some reasonable time?
Yeah, you're right. That's true. That's a great question. The simulation that I showed you is one of the simulations that has been done. There are many. We didn't do the simulations. The simulations are very, very complicated, and they are done with clusters of cores, clusters of computers. And this is one of the simulations. We use the Jevolution simulation, which uses 16. In our calculations until here, we use 16 cores of computer, and it takes about 1 minute or 1 to 2 minutes to complete one simulation.
Okay, thank you. And are you aware of any, because you are taking into account gravitational interactions, and do you also incorporate general theory of relativity? And do you need to apply any approximations during your calculations? And can you name them, maybe?
Yeah, we use the general relativity. There is another option to use the MOND, the modified Newtonian gravity, but we use the general relativity, and we take the assumption of weak field expansion. weak field of gravity, and we expand it in this space.
Okay, thank you very much.
Thank you for your questions.
Okay, thank you very much for your presentation, Dan. Now, proceeding to the next speaker, we welcome Agas Mahajan and from Delhi, from the Indian Institute of Technology. And the topic will be relatively curved particles from geometry to relativity.
Yep. Am I audible?
Yes, yes, you're on. Hello.
Hello. Hello, is this visible? Other side.
Yes, we can now see your presentation. Okay.
Okay, so yeah, good evening to everyone present here. So I'm Agas Mahaj, an undergraduate in the Department of Physics and Indian Institute of Technology, Delhi. I'll be talking about the connection between geometry and special relativity. Don't worry if you maybe do not get some of the proofs, but the ultimate will be that these two theories are very intrinsically connected. So let me start off with some axioms. Consider V to be a set of points with one-on-one correspondence with all the velocities. An arbitrary point represents the reference frame, and position vectors of other points are the velocities in that frame. For instance, C is a reference frame, and then the vector CA, this will give you the velocities of A with respect to C. Now the thing is, since many objects in the universe have the same velocity, each point is sort of a herd of objects with the same velocity. So, taking any object inside the point A and any object inside the point B, the V distance between these 2 points will be intuitively the relative speed of the 2 objects. And also the V collinearity of 3 points, A, B, and C gains. If some objects at B and C meet the object at A, then they all necessarily meet. This is a simple exercise that I would advise you to try to figure out the proof on your own. Now, our definition of xy, which is the velocity of y with respect to x, leads to the normal velocity addition, which is the Galilean addition. I would say in a normal addition, if the v distance satisfies AC plus CB equals to AB, the normal addition, where C is a point on the segment A. Now we are contradicted here by the second postulate of special relativity. Why? It's a trivial reason. I would advise you to think for yourselves. So that is why we need another function. We need to choose the R, that is a distance between A and B, to be a function of the relative speed of B with respect to A. Right. In the previous case, the function capital R was just the identity, but we need something else. We need another function so that we aren't contradicted. And obviously, we take the normal addition rules, the distance between A and B, where C is any point on the segment A. Now I'll try to show you that the 2D relativistic velocity space is nothing but the hyperbolic plane. If you haven't heard what a hyperbolic plane is, don't worry, that's just a terminology. So consider any observer located at point O in the velocity space described before. And now the observer looks around and makes a map of all the velocities he sees. So the map drawn by the observer, I'll denote it by MO. That drawn map is nothing but a circle with center at O and the radius C, where C denotes the speed of light. This is so because the absolute speed is C by the hypothesis of special relativity, and so it will form a circle. One thing to note here is that 3 collinear T points lie on a chord of the circle. This is not a trivial exercise, but I won't spend my time proving it here. You can take it by considering any 3 uniform objects and 2 of them meeting each other. So now these previous assumptions were rung the bell, or if not, then it is nothing but see that relativistic velocity space is mapped on a circle, so that V lines are mapped into chords of the circle. We are considering a circle and its chords, and that is just the Klein model of the hyperbolic plane. The only thing left to prove is that V congruent segments in velocity space are depicted as segments congruent in the Klein model. The V segments, AB and CD, we know that they have equal V lengths if velocity of B with respect to A is equal to the velocity of B with respect to C. That is because of the definition chosen of the velocity space. And in the Klein model, 2 segments are congruent under an isometry, which is just a transformation which preserves the distances. So my only job left is to show that the K, I will take K as the non-Euclidean distance between A and B. And my job is to show A and B is a function of the relative speed of B with respect to A. Here's a short proof. Consider this MO, the map drawn by the observer O is the center. Now take any arbitrary point A and consider a transformation which takes a point X on the circle and maps it to a point X prime such that OX prime is the relative velocity of X with respect to K. For instance, taking the point A itself, under this transformation, A will be mapped to an origin because the relative velocity of A with respect to K is 0, so that's why it's on the origin. So writing A prime as O, we can express this transformation as A prime X prime.
I think that some technical errors occurred. Yes, hello again. I think that you disconnected for a little bit.
Yeah, sorry. Is this visible?
Yes, now it is visible.
Okay, so sorry for the. So yeah, as I was saying, the transformation will map the point A into the origin. So we'll write A prime for O, and we can express this transformation as A prime X prime is equal to the velocity of X with respect to A. And if for a moment we ignore the primes, we see that this is nothing but the relation of the map MA. The map MO was mapped by the observer. MO was by the observer at O, and this is by MA, the observer at A. So we see that the mapping, this transformation is nothing but isometry. And so we have K as, we remember the non-Euclidean distance, K of A comma B is K of A comma B prime, which is the same as K of O comma B prime. And now observe that let P be any point as shown in the figure, P be any point other than B prime, such that OP is equal to B. Then that can be derived from OB prime by just a rotation. So again, the distance is preserved. So K of O comma B prime is K of O comma B. If we let R of V, the R is the function which we were finding. If we let R of V equal to K of O comma P, then we get K of A comma B by this chain of equalities equals to the R of V of B with respect to A. And that is what we had started to do. And so, the relativistic velocity space is so to find the actual formula for this distance, I will transform this Klein model into another model of non-Euclidean geometry known as the Poincare model. It's a simple, standard transformation. I won't delve on how you derive it. You can see from this example that A is mapped to A prime, B is mapped to B prime. The thing to note here is that this thing known as a cross ratio. This is a cross ratio of AB and A naught B naught. It's this ratio of two linear fractions. The cross ratio of AB, A naught B naught is the square of the cross ratio of A star B star, A naught B naught, where A star and B star are the images of the points A and B under this transformation of the line to the pointer model. Another thing which you might have come across or might not is that the distance between 2 points A star and B star in the non-Euclidean plane is given by the logarithm of this cross ratio. Now, the thing is, if I finally put the K of A comma B as the distance between A star and B star, which is equal to half of the logarithm of this cross ratio. Half because this was the square I'm taking out, so you can take it out of the indices and we get this expression. We get this chain of inequalities. I'll now be taking the speed of light as 1. I'll just scale it down for the easier formula. And by taking K of A comma B as K of O comma P, which was shown in this chain of equalities before, we see that the cross ratio of OP and U, the visual interface that I use, UV are the endpoints of this segment. By taking into consideration the cross ratio, finally we get R of A comma B is equal to half of the logarithm of 1 plus B upon 1 minus B. This R is the distance between A and B. The thing is, solving for B, we will get finally the velocity of B with respect to A as the hyperbolic tangent of R of A and B. That is one of the main results of this model we have taken. This was shown by Minkowski in 1908. That we can transform any relative into just a 2D geometrical problem by deriving this formula. And using this, you can prove many formulas for relativity. I'll just show you a simple one of the velocity addition. Consider B moving with velocity V1 with respect to A, C with V2 with respect to B, and C moves with B with respect to A. Let R1, R2, and R be the corresponding rapidities. The rapidity is nothing but the R of A comma B. That is the distance. So by taking B as tan hyperbolic of R, because that is what the definition is, and R is given by R1 plus R2. By using the standard addition formula of hyperbolic tangent, we get the following formula for the relativistic velocity. There should be a c-square factor here, but as I said, I have taken c to be 1. If you try it out by taking c, a factor of c-square will come up here, and that will give you the familiar expression you are equated with. And that brings me to the end. So this the interested listener, and try to look at these books, the geometry of space-time. These all are books which are connecting physics and geometry. It's a very interesting field to look into. This Geometry Illuminated by Heart is one book I would suggest if you have never come across the hyperbolic plane or non-Euclidean geometry. It gives a pretty decent introduction to these subjects. So that's it.
Okay, thank you very much for the presentation. Are there any jury questions here, or maybe some participants? Okay, if not, I think that we can move on to the next speaker, as the time is pretty stiff here. So next we have Adriana Borrego-Quintana about dark matter halo shapes from fit to spark galaxy rotation curves. And the speaker is from the Complutense University of Madrid in Spain. Are you with us? Oh yes, hello.
I am. Can you see my presentation?
Yes, we can see it.
Can you see me?
Not yet, I think, but maybe it is
Well, then
an
the
error on my
camera
part.
might not be working.
Yeah, maybe it will sort itself out during the presentation.
Okay, then I shall begin. So, good afternoon. My name is Adriana, and today I will be giving a small talk about dark matter halo shapes according to rotation curves from the fits of the galaxies of Spark's database. So first I will introduce the problem of galactic rotation curves. We will want to study the rotation curves of galaxies, and for that we will study the path baryonic matter follows. And for that we will use the balance between forces, centrifugal and gravitatory forces. So according to the equation we obtain, the velocity should decrease as far as we get away of the center of the galaxy. This would be the blue lines in these graphs. But as we see, experimental data that are the black points show that real rotation curves flatten as we move away from the galaxy. A way to explain this would be to propose the existence of dark matter halos that surround galaxies and that interact gravitationally, not only with those galaxies, but also with other halos. And the interesting thing is that when those halos interact between them, accretion occurs along a privileged direction and in a clumpy way, which leads us to think that dark matter halos have a more elongated or ellipsoidal shape rather than a spherical one. So throughout this project, I have studied these galaxies. First, I've calculated the potential, then the gravitational field, and from that, the rotation curve. So the first model I will want to study, we will consider two classes of shapes according to the triaxial classification. A more prolate shape, an elongated shape, in which the semi-major axis will be along the z-axis, and a more oblate shape that would be a more flattened gravitational source, in which the semi-major axis will be around the x and the y-axis. So I will study first an extreme case of the ellipsoidal halo, this cylindrical halo. So assuming the gravitational source has a more cylindrical form, we will be able to calculate the gravitatory field as we study the flux among the surfaces. And from that, we will be able also to study the rotation curve. As we see, depending the rotation curve inside of this cylinder will depend on the density profile of the dark matter. But as we move away from the dark matter halo and we are outside of this dark matter halo, we will see that the rotation curve flattens. It reaches a constant velocity. And this is the case of, in these graphs, we see two galaxies in which the cylinder would end here, where the flattening begins. And the next would be study the ellipsoidal halo. For this, we will use a mathematical tool known as multipole expansion, through which we will approximate a function, in this case, the potential. And for that, we will use, we will express the potential in terms of the azimuthal and the polar angle. We will then impose a series of physical conditions on the potential that will be the ones seen in the slide: symmetry under rotations around the z-axis and under reflections on the galactic plane. And in this way, we will be able to calculate the rotation curves and fit the different galaxies from Spark's database. So it will depend a little bit on the shape of the rotation curve. When the flattening of the curve, when we obtain when the constant velocity field is reached near to the galaxy center, like in this galaxy, we will need to use multiple expansions of higher orders. In the other case, when the flattening occurs maybe far away from the galaxy, like in the first place, we will use maybe lower order expansions. Maybe we will use expansions until and the quadrupolar terms, monopolar and quadrupolar terms. Now we will regard the case of the internal contribution to the potential, and we will be able to find a relation with the inertia moments. In this case, if we are considering a prolate halo, then the semi-minor axis, the length of the semi-minor axis that are C and B, will have the same inertia moment. But the difference between the inertia moment along the semi-major axis and one of the semi-minor axes, it will be negative. It will take negative values when the halo is elongated or prolate. In this slide, we can see how the different models that I have studied are labeled, and we will grade them with marks from 1 to 9, where 1 is the better punctuation a model can have. And we see that the models that have that are more elongated, like the cylinder or maybe the higher order expansions, will have better grades than the one which considers the halo to be a sphere. Returning to the point of the study that related this axis with the potential, the inertial moments and the potential, I said 2 slides ago that when this difference between inertial moments was negative, the halo would have a more elongated shape. And this is indeed what happens, because the majority of the galaxies show a negative value of this difference. Then we can also measure the approximation of the value of the length of this semi-axis, and we will see that most of them will lay on the left side of which would be a sphere. What I mean saying this, that when the points end on this line, then the halo will have a tendency to have a spherical shape. And when it's in this part of the graph, then it will have a more ellipsoidal prolate shape. And in recent studies, using numerical simulations of dark matter halos and interaction among them, it has also been calculated a rate that is the rate between the semi-minor length of the axis and the semi-major length. And the values that have been reached in those recent investigations are values between 0.5 and 0.7. In this case, I have reached values of between 0.3 and 0.6, which means that the halos, the found halos, should be very elongated indeed. So in the light of the above, I would say it is not possible to leave out the possibility of elongated halo shapes rather than ellipsoidal, flattened ellipsoidal. I mean, these ones, they have a more prolate shape. And as has been seen in this study, the tendency in this database is of more prolate shape halos. So this is all. Thank you for listening.
Thank you very much. So I will first ask whether there are any questions from the jury or from the participants. And
I have one question, if I may, again. So I didn't catch that. Maybe if you said it, then I'm sorry. But can you tell me how many parameters are there in the model that are fitted, that are, you know, in order to fit the theoretical data to the experimental ones? Do the number of parameters vary when it comes to those different models, the different shapes that you have been using?
Well, I have these different models in which all of them are the expansion of the potential, and then I have also the cylinder model. In those, I use two types of density profiles. That would be the Saxon-Wood density profile and a constant density profile. Each of these models have this number of parameters that have to be fit. So this one has 4, 3, but maximum 7.
Okay, so we do not see this tendency that the more fitting parameters do you have better agreement between theory and experiment. So it's not the matter of number of fitting parameters, but some more some other stuff. Okay, thank you very much.
I also thought that if I put more free parameters to fit, then the fit would be better.
Yeah, that would be the obvious situation.
But it is true for the potential expansion, as you see, 7, 5, 4, 3, and also in the cylinder model 4, 3. But the thing is, cylinders work better than expansion, potential expansion. So thank you.
Okay, so it's not just the trivial case of increasing the number of fitting parameters, but it's something else. Okay, thank you very much.
Else. Thank you.
Okay, and I will have one quick question. Could you maybe go to the slide where you showed us the two plots and one had this line corresponding to a sphere?
Yeah, this one?
Okay, because maybe I didn't catch it, but is there a reason why the points, because I understand that points that are under this yellow line correspond to oblique.
Yes.
Yeah, okay, so when they correspond to oblique halo, why is it only visible when we use when we include the quadruple term?
Well, this is something I have been studying, and I still have not reached a conclusion of that.
Okay.
But I am sorry, I cannot answer for now.
Yeah, I just thought that it is an interesting result, that because it is very visible here that
yes, it is.
Yeah. Okay. So thank you very much for your presentation.
Thank you. Goodbye.
And goodbye. And
Thank you.
Now our last speaker during this session, Fatma Nouri from Sharif University of Technology in Tehran. And a presentation will concern Hawking information paradox.
Hello, can you hear me?
Hello. Yes, loud and clear.
Actually, I have a weak internet connection. I'm afraid I cannot share my screen and use camera simultaneously, so I just share my screen. Can you see my screen?
Yes, we do.
Okay. Well, hello again. I'm Fatima from Iran, and I want to talk about the black hole information paradox. First, I want to talk about what is actually a black hole. We are pretty convinced now that black holes exist. Here you see the first image of a black hole. Once imagine a star is collapsing under the force of its own gravitational field. So as time goes by, its radius shrinks, and eventually it enters into its Schwarzschild radius. This radius separates the black hole interior from the rest of the world. It is also known as the event horizon. One interesting fact about the black hole is that light cannot escape from inside the horizon. Also, there is a singularity in the middle of a black hole where the curvature of the spacetime is divergent. Now I want to give a bit of motivation about why we study the information paradox. Actually, we do not study this phenomenon for its own sake. We seek a greater issue, the theory of quantum gravity. Classical general relativity, which means a decoupled limit of general relativity and quantum field theory, is not a complete theory of gravitational phenomena. It predicts that if you set an initial data in gravity and let it evolve in time, eventually it will reach a situation where you have a very large curvature of space-time on a very small scales that quantum mechanics is important. Classical GR breaks down at this regime, and we need a theory for quantum gravity, which we do not have yet. An example of this regime is the black hole singularity. So it seems that the study of black holes helps us to find the theory of quantum gravity. Before going further, I want to define the semi-classical regime of gravity. It is the weakly coupled limit of general relativity and quantum field theory. We need a strong coupling of these two theories for quantum gravity, so we can say that semi-classical regime, which is weak coupling, is somewhere between classical GR and quantum gravity regime. We expect that this regime works at a small curvature of space-time, like at the event horizon, although we are surprised because the black hole information paradox states that we may need input quantum gravity to understand physics at the event horizon, where we normally expect semi-classical gravity is valid. That's the reason we use the word paradox. We cannot talk about the information without talking about the entropy. So I'm going to explain the black hole entropy briefly. It was believed that black holes have no entropy because classical general relativity states that black holes have no microstate. Until Bekenstein came up with this solution. Black holes are thermal objects. They have a temperature and they do have an entropy. It's just that this entropy isn't due to classical GR. It's due to quantum gravity microstates, and it is given by the area of the event horizon divided by 4 g Newton h bar. So yes, maybe GR doesn't have microstate for a black hole, but quantum gravity does. Furthermore, for a black hole close to equilibrium, we expect a temperature that is inversely proportional to its mass. Since black holes are truly thermal, they should radiate. Suppose the temperature of a black hole is hotter than its ambient surrounding. In this case, as it radiates, it shrinks in size, losing mass, and due to this relation here, it gets hotter and evaporates faster until it's completely gone. Well, what is the information paradox? To be more specific, the black hole information paradox is an apparent contradiction between the predictions of semi-classical gravity at the event horizon and the unitarity of quantum mechanics. So again, this is the regime that we expect there is no problem between the GR and QFD. Because they do not talk to each other very much, means they are weakly coupled. But the black hole information paradox is telling us not actually, apparently they do, and that's very surprising. We can see the paradox like that. Imagine we have two observers, Alice and Bob, who are entangled and they are in a pure state, which means that we know the exact quantum state of them. Alice ends up in a black hole while Bob does not. If the black hole evaporates entirely, then Alice is gone from the universe. And what seemed to happen is that the information is lost. What I mean is that the initial state of our entangled pair is known. For example, this psi state that I wrote here. Then the left particle, Alice, falls into the black hole, and after a complete evaporation, what is left is just that Bob, which has a mixed state, proportional to identity. So now we do not know the exact state of our system, while we knew it at first. Therefore, the information is lost somewhere between the initial and post-evaporation state, which is a gross violation of the unitarity of quantum mechanics. I'll explain in more detail a few minutes later. So to see the information lost between the initial and post-evaporation state, one thing which is very helpful to do is to talk about the entropy of the black hole radiation, also known as Hawking radiation. We call it von Neumann entropy, which is defined as minus rho log rho, where rho is the density matrix of our system. Why do we use this quantity? Well, it has some nice properties. First, it is invariant under the unitary evolution. So for testing whether we have unitarity, we could test whether this thing remains constant or not. Also, it vanishes only for pure states. That's also very nice because if we start at a pure state and evolve unitarily, we must end up with a state whose entropy is zero, which means the final state must be pure too. And finally, it is bounded from above by the entropy which Bekenstein defined the thermal entropy. We can roughly quantify the information in a state in terms of difference between the thermal entropy and von Neumann entropy. Due to the last property, information is always greater than or equal to zero. Because the thermal entropy is at equilibrium and essentially has no information content, if a system evolves to progressively larger von Neumann entropy, then this difference is shrinking and we are losing information of the system. One can complain that this happens all the time, that you have some typical experiment and your system begins at a pure state and eventually it ends up in a mixed state. And the reason is that it is interacting with its surrounding. An open system interacts with environment and it will settle down to a mixed state and it will lose information. Of course, this is not a violation of quantum mechanics because open systems just do not evolve unitarily, but we do expect that closed systems do. The entire universe is not an open system. In this case, we assume that we can neglect the interactions of other objects in the universe. They are too far. So our system contains the black hole and the entangled pair is a closed system and it have to respect the unitarity. It starts at a pure state, so it must settle down in a pure state. As I mentioned before, the von Neumann entropy have to remain zero. In case of our entangled pair, their initial state was pure. The von Neumann entropy was zero. And after evaporation, one can prove that the entropy is equal to log 2. So we don't have unitarity. Here you see a more pictorial way of thinking about this paradox. Before the black hole starts evaporating, everything is at pure state. Since, as I mentioned, the interactions of other objects in the universe are too weak to consider, the entropy is zero. This entropy, I mean, is zero. Now, as the black hole evaporates, we can think of this in terms of this entangled pair. The entropy of radiation, which we called Hawking radiation, increases. It increases. But that's okay. For now, we have two interacting parts, the black hole itself and the radiation. Together, they are pure. But when we look at just one of them, it has a mixed state, so it is normal to have a non-zero entropy. As black hole continues to evaporate, the radiation is going to keep on increasing until the black hole disappears. So all we have left is just the radiation. And now we don't have the excuse anymore that the radiation is just a part of an interacting system. Now the radiation has a mixed state and also a non-zero entropy. And there is no other subsystem to blame this on. We have lost information in this process. And this was Hawking's calculation in 1975. Still, we expect from unitarity to have a zero entropy at the end. The unitary curve, the purple one, also known as page curve, has to go up. And at the page time, again named after Page, who first proposed it, it must go down to zero. But how can we explain this decreasing in the radiation entropy? We are in a very exciting time period regarding to the black hole information paradox. Last year, some physicians introduced a calculation using something called holography, which can solve this paradox in 2 dimensions. It is not clear how to expand this calculation to 4 dimensions, which our universe is, but it seems that we can expect impressive progress in near future. Well, I hope you enjoyed this lecture. Here is my references, and thank you for your attention. Any question?
Well, thank you very much for the talk. Are there any questions from the Zoom participants?
I would like to ask something about the very end of your talk, when you said that there is a calculation based on a holography, yes, which can shed some light on this paradox in the 2D case. So could you maybe give us some more detail or some sort of intuitive feeling of yes, what is the resolution of this paradox in this case?
Yes, I can somehow. You see, due to quantum field theory, at the event horizon, the particle and antiparticle in the vacuum are created. Okay, the antiparticle goes into the black hole, but the particle goes out. We see the particle as radiation. Okay, and they say that at T page, these antiparticles reach to the inside the the origin of the black hole. They create an island there, and because the vacuum state at the event horizon, the moment that this particle and antiparticle created, they are entangled to each other. So half of them creates an island and the black hole, and the rest of them is out in the universe, and they are entangled. And from T page, we have to consider their entanglement. And this entanglement decreases the entropy of radiation. Yes, and it would follow the unitary curve.
But from what I understood, the part of the paradox is that from the outside, such a Hawking black hole just emits the thermal radiation, so that it is impossible to differentiate between different black holes. But from what you are saying, it seems that depending on what has fallen into the black hole, the entanglement state of this black hole can be different, right? So
yes, I think yes.
Okay, thanks.
You're welcome.
Okay, thank you very much. Then, are there any more questions?
I have one more, if I may.
Yes, please go ahead.
So since I'm not an expert in this field of black holes, this might be a trivial one. But you said that those black holes have entropy and temperatures, so they emit radiation, due to which they seem to evaporate because their mass is decreasing and temperature is increasing. So what is actually, and at the beginning you said that there is this event horizon which can't be passed through by anything, even light. So how come this radiation emitted by the black hole is able to pass through the event horizon, and what is the physical nature of this radiation? So is it what kind of radiation is it? Is it electromagnetic radiation or some other kind?
Well, you see, this radiation doesn't come from the inside of black hole. You know, at the event horizon, okay, the particle and antiparticle is created from the vacuum. Okay, we have a particle and we have an antiparticle. Okay, the particle is the radiation. You see, they are creating simultaneous. Always they are creating. Okay, so these particles are radiation, and the antiparticle went into the black hole. And so the nature of the radiation is just particle. You know, they are small. So yes, we can see them as an electromagnetic. I think they have both.
So these are particles just flying out of the event horizon.
But you see, particles have both wave nature and particle nature.
Yeah.
So.
Okay, thank you very much.
Thank you very much. And I think that would conclude our theoretical session, our first theoretical session of the conference. So thank you very much, everyone, for tuning in. And I encourage you to join us at 4:30 for our keynote speaker, Serge Galam, and he will give us a talk about sociophysics. So a warm encouragement to tune in at 4:30. Thank you very much, everyone, once again, and see you soon during the other sessions.
Thank you very much. Goodbye.
Thanks, bye.
Bye, thanks.
Okay, good evening, everyone, at the day 3 of the Kumquat Conference. I welcome you after the coffee break. And now I have an honor to introduce our next keynote speaker, Professor Serge Galam, a physicist specializing in sociophysics, disordered systems, and collective phenomena. First, a quick preview of his career. He obtained a PhD in physics at the Pierre and Marie Curie University in Paris, and later on at the Tel Aviv University. Before returning to France, he taught at the City University of New York and at the New York University. In 2003, he joined the Center for Research in Applied Epistemology of the École Polytechnique. And in 2013, he became a member of the Paris Institute of Political Studies, widely known as the Science Po. A scientist emeritus at the French National Center for Scientific Research, widely recognized as a pioneer and a father of modern sociophysics. And a quick tidbit on his recent work, that he correctly predicted the 2016 US elections, approaching the so-called Trump phenomenon from the social physics point of view. And although the model mispredicted the recent 2020 elections, the error was within a very small margin. And today we are pleased to welcome Serge Galam at our conference and learn about the hidden archaic mechanism driving opinion dynamics. Professor Galam, I welcome you, and the floor is yours.
Thank you very much. I'm very happy to be able to give you this lecture and to exchange with a student. You are the future of research, so it's very important and stimulating. And thank you for inviting me to make this presentation. So now let me first go to sharing my screen. You did not allow me to share my screen.
Now you're allowed. Now you can.
Okay, so let me...
Sorry for problems.
Now you see it?
Yes, it is visible for us.
Okay. So I will make a presentation of the basic model I've been developing for many years, 4 decades actually. It's amazing how time passes. And in case I am not able to go up to the end, it's not a problem because it's go by step, like in a sandwich where I am adding different elements. So you will be able, it's better to well understand even only the first one and not to run over the whole element which creates the model. And so the title, The Hidden Archaic Mechanism Driving Opinion Dynamic, is a kind of, all these studies has been leading to unfortunate outcome and result about what would be at stake when we think that we are having free debate. And I will show you why and how with this modeling, which it's important to say it's a modeling, and for the moment it's not, of course, a proven theory. So what is sociophysics? It's the use of concept and technique from statistical physics to describe some social and political behavior. It's important to mention that it does not aim either at an exact description of the reality, nor to be a substitute to social sciences, but indeed it aimed to provide an additional, different, and rather counterintuitive vision of the social reality. It's important to warn that the goal is neither to create metaphors from physics, because I think this is misleading, and many people in the past has been trying to do this kind of thing, nor to make statement in the name of scientific authority. The challenge is learning from physics to build specific models the way physicists do. In short, sociophysics is not a metaphoric approach, it's not a mapping approach, it's not a narrative. It is building social models from first scratch with crude approximations the way physics proceed to get meaningful insight in the social reality. Where it comes from, so as I say, for 40 decades, I have been working on this field, and indeed, among the first paper was one in 80 in which I was calling to the physicists to act like a revolutionary catalyst to modify our view of society and social phenomena. I have also a warning about what would be a kind of imperialism of physics. This is in 82. I think most of you were not born yet. And in 82, I had a paper on entropy, disorder, and individual freedom. And this is, I consider, like a founding paper of 82, in which we quote actually the term sociophysics, a new approach of sociological collective behavior, with Yuval Geffen, which is in Israel, and Jonathan Shapir, which is in the States. We were three of us at Tel Aviv University in the physics department at that time. It's also important, as you are a student, to mention that today sociophysics, like all interdisciplinary physics, sound very nice and exciting, but this was not the case in the 80s. Important to know that at those early times, physicists were adamantly hostile to sociophysics with total rejection. It's very strange. I never really understood why, but it was a fact. And an anecdote, but which is very meaningful, even if it's very hard to imagine, that our first research manuscript, the one quote with sociophysics, has been locked in the chairman office of the Department of Physics at Tel Aviv University. This did happen 40 years ago. Hard to imagine. If you would like to know a little bit of the history of this early difficult time for sociophysics, you can have a look of this very short paper, Sociophysics, a Personal Testimony, in which I count all these stories. Econophysics came many years later, and then it was accepted, and then sociophysics started to get accepted. So today, sociophysics deal with a rather large spectrum of problems, including group decision-making, coalition forming, terrorism, radicalization, fake news, marketing, intelligence, hierarchical system, finance, social network, and more elements. So a very active field. But one main topic is opinion dynamics. Opinion dynamics today is a major decisive key in both democratic and even non-democratic countries. It is instrumental in driving public debate when the issues at stake are not based on total, full knowledge, like we are now facing, for instance, with the COVID and the vaccination question, people which are against, to impose it, to make it mandatory or not. And often it's connected to political decisions which are required on this topic. So it's very important to try to, do we understand opinion dynamics, or does our current understanding correspond to the reality of opinion dynamics the way it works? We will see what this model can show. And indeed, a major issue which is connected to these political issues is why, while most political issues which are raised by tiny minorities in social media stay most of the time confined to this tiny minority with no consequences, and sometimes for no apparent reason, one issue all of a sudden emerge and at once and become a major public issue, challenging the current situation, even putting at stake policymakers by surprise, and sometimes it can go up to a destabilization of the associated political institution. Why this happened for very few and not to most of them? In addition, policymakers need to rely on public opinion to legitimate some decision, in particular, for instance, like with the vaccination, like with the lockdown, when we are now facing with the COVID. So it's important to have the support of the majority of the public. So the public debate will fill up the missing part of the available data to end up with a complete view saying, yes, we should go, we should make it mandatory or not. It's also, of course, applied to the case of election, and then it's very important. Can we predict outcome of election? Can we twist manipulation of election before, not the election itself, the fact to vote, but the making of opinion dynamics prior to a voting? Yet today, the current paradigm is that the dynamic of opinion is an essential feature of democracy, which is true, because it allows individual choice to aggregate into a majority will. And if I would question this statement, it's immediately associated with totalitarianism, because one of the first making of a dictatorship is always to reduce drastically the freedom of choice and discussion. However, the fact that dictatorship use this restriction of freedom of discussion does not prove that the dynamic of public opinion obey a democratic process in the sense that it preserves the choice of individual. An hypothesis is to find out maybe the forming of public opinion toward the aggregation of individual view about an issue along a predetermined direction against people's free will choice. So this is not a dictatorship want to oblige people to think along a given direction. The hypothesis here is to say that we have archaism in our mind, in our view. Our education, our rational thinking allow us to depart from this archaic view. But the question is, do these archaisms are still working when we engage in a public debate? It's important to mention here that I am not dealing with a choice being wrong or right. I am not advocating for one candidate or another in case of an election. I am focusing on identifying the hidden mechanism which drives the dynamic of opinion between two competing choices to anticipate the one which will eventually end up above 50%, winning an election or imposing some new way of life, of new behavior in the society. My major assumption is that the mechanisms involved in the making of opinion dynamic are universal and apply to all issues, independently of the content of an issue. So the so-called Galam model make separation between two separate mechanisms. External mechanisms which are acting directly on single individual, like TV, media, publicity, external event, which can be a terrorist attack or bombing or a climate catastrophe or whatever, but it's something that an individual cannot react back to it. He just have it, feel it, and this not automatically will make it change opinion, but sometimes yes, sometimes it will resist. And then internal mechanism, which is the way people discuss among themselves, and this can change opinion of a given agent or many agents or not. So the model, the basic model, considers two discrete choices, A and B, which are competing among a community of agents. For instance, Brexit, yes or not, to vote Clinton or Trump in 2016, Trump or Biden in 2020, wedding to all, recently we had it in France, I think also in Poland, or vaccination, mandatory or not, to the green pass for vaccination, many other issues. It's possible to extend the modeling to three choices. I did it in 2005 with Galam and Relativity. It's much more complicated analytically, but in principle, it's possible and even to more than three choices. I consider heterogeneous agents with three psychological traits. The main one are floaters. Floaters are agents having an opinion and advocating for it, but they are susceptible to shift opinion if given convincing argument. So these are rational agents which want really to make the best choice. Then I have inflexible or stubborn or committed agents. These are agents who never shift their opinion. For whatever reason, they stick to their opinion and only advocate for it, but they don't listen even to argument against their choice. They keep to their choice and they want their choice to win. Contrarians are agents which are taking the contrary choice to the local or global majority, independently of that choice itself. There are not too many of these people, but we all know, and it depends on the issue, where sometimes you just like to oppose the majority, not because you defend or you are against what the majority is choosing, but just to make a point to develop a minority view. So the modeling that what we want to understand are these internal mechanisms. So we consider at some point that we are turning off the external effect. Then at this moment, we have initial support P0 for A, 1 minus P0 for B, and then we turn on this internal mechanism and we study the dynamic driven by this internal mechanism. How does it work? People are discussing within small group. It's open, informal, free debate. And then while discussing the issue, some agent may change their mind. How? This is very complicated cognitive, psychological, sociological process, and it's even not known yet what make all of a sudden someone change in mind. So when we are facing a complicated problem, we make it the physicist way, which is simple. We simplify at maximum the question. The way I do it is to say, okay, let's consider that these complicated mechanisms are equivalent at the end as one person, one vote, and local majority rule. This creates a local group polarization when people discuss. Of course, it does not apply to stubborn, which do not shift opinion, and contrarian shift against the majority. So the dynamic work having a starting initial condition. So we have, as we mentioned before, P0A. However, within this P0A, we have little a inflexible. So we have A inflexible and P0 minus A floater. For B, it's 1 minus P0B with little b inflexible and then 1 minus P0 minus B floater. So we iterate the dynamics by randomly distributing agent in small group. Within this small group, we update locally agent according to majority rule, so not too inflexible. Once this is done, agents are reshuffled and distributed again randomly in small group, and then we repeat this so on and so forth, 1 times, 3, 4, 5, 10 times, depending on how long the debate, the public debate is going to last. However, each one of these local updates modifies the respective proportion, P0 to P1, to P2, to P3, and then we would like to be able to predict where it will end up, beyond, above 50% or below 50%. This is an illustration. I have a group of agents, A, B, capital A and B, these are the floater, small a and B, these are the inflexible. Then we distributed them in this small group of 3, 2, 4, 5. We apply to all of this group local majority. So here I have 2B, 1A, this go to 3B because they are all floater. But you see here that I have 3B against 2A, B win with respect to majority. So the floater A move to B, but the inflexible A or the stubborn A stay A. And we do it for any composition of group. However, something happened here. If I have a tie in a even size, here I have 2 people, 1B, 1A, they are both floater. What to decide? local majority cannot apply because there is no majority. Now we get into the interesting part. What to do when there is no majority in a local group? A physicist would decide that at a time, nothing happens with no update. We say, as there is no majority, nothing happens, so I redistribute the agent as if nothing had happened. However, here we are dealing with human. And indeed, the interpretation is at a time when there is no majority, I can say that it means that the collective confrontation of individual opposite argument is balanced. All the two choices get the same weight, the same amount of argument in their favor. And then this creates a state of doubt among the agents which are at a tie. And then when a group is doubting, since rationally both choices become equivalent and rationally cannot operate to make a choice, usually when we are in this situation, we say, okay, let's, like flip a coin and take it randomly. So it's a metaphor, we in an image, it's not a metaphor in the model. I say we should not do it before, but here it's what happens, say, let's take it randomly. And then it is as if we are flipping a coin. And my main hypothesis at this stage is that indeed the flipping coin is biased along the prejudices which are activated spontaneously and unconsciously by the issue at stake. But it is perceived as it is by chance. So if in a given social group, the distribution of heterogeneous prejudice favor A or B with a probability K, let's say it will favor A, and 1 minus K, B. So when we are at a tie, 2A, 2B will go to 4A with probability K, and to 4B with probability 1 minus K. Prejudice of a given social group are diverse, multiple, and mainly unconscious. Of course, we have people which will state their racism, their sexism, their homophobia, but many of other people say, and they don't want to be racist, they don't want to be homophobe. However, it does not mean that they don't have in their unconscious these prejudices. It's also important to notice that different issues raise different prejudice among the same group of people. Here is an illustration. I am at a tie with a given group of people, and then the decision is about high-tech technology or fashion. In all these cases, at a tie, at doubting, no rationality to decide new product or old product, the tip will go to the novelty. We say, okay, let's take the new one. Let's take the new computer, the new car, the new TV, if they're equivalent to the old one. However, if the same group has to decide about a reform proposal, for instance, changing something in your life, in your way of working, if we are at a tie, the tip will automatically go to the statu quo. We prefer to keep what we have, what we know, and not to move to something that we yet don't know and which has no a priori more advantages than what we have before. It's important to notice that at a tie, the aggregation of information neutralizes the information content to make a decision. So this is counterintuitive, since normally we expect the more information available, the more documents should be the making of a choice. So this is a nice illustration of how this kind of modeling, the way physicists do, can produce very complicated cognitive feature from a very simple model here, because this doubting process, prejudice effect are very complicated phenomena. So now, in order to really now understand what is the consequence of this hypothesis, we have to frame the problem with equation. When we do that, this reveals a nonlinear dynamics driven by tipping point, but not always. Up to recently, I could only treat small size group because I like to solve the problem analytically in order to really understand what's going on. So I could consider only one psycho at a time, in addition to floater, which means floater and contrarian, floater and inflexible, but not everyone, and only for very small size group, 2, 3, 4, up to 5, but not for larger group. But last year with Taksu Sheon from Japan, we could get analytically an update equation for any size with any combination of the 3 psycho and prejudice. So indeed, we were able to get a universal formula in 5 dimensions to get the update dynamics. In this talk, I will treat only group of size 4 because it's very kind of simple, not so simple, but not too complicated. And here is the update equation where I have a proportion P for supporting opinion A, little a proportion of A stubborn, little b proportion of B stubborn, C is a proportion of contrarian, and K is a proportion of prejudice in favor of A. Then we need to solve the fixed point equation P1 equal P0, and this will define the associated dynamics. The prejudice, inflexible and contrarian share the feature to create a tipping point dynamics. However, the inflexible and contrarian have the peculiar property to be able to, above some proportion of their presence, to substitute a single attractor dynamics. And this is a major qualitative difference. Why? When I have a tipping point dynamics, it means I have a tipping point separating 2 attractors. Then I can predict easily the outcome. If the initial proportion A is below the tipping point, A will lose the debate. However, if P0 is above PC, A will win. So once PC is determined, you need a pole, and then to know if you are above or beyond PC, and then you can identify and predict the winning attractor, so the winning choice with for respect to the issue at stake. So however, the work, I would say, from A supporter or B supporter is to the challenge to be above the threshold. So you can win or lose depending on this prior work you had been doing on individual separately. However, when I have a nonlinear dynamic driven by a single attractor, whatever the conditions are, initial conditions are, the dynamic will lead to the single attractor. So then if the attractor is below 50%, A will lose. If the attractor is above 50%, A will win. But there is nothing to do once the conditions are given, no matter of acting on the initial condition. So let's see now how it works in more detail. And then I will separate the effect first to have the prejudice effect with floater, so no contrarian, no inflexible. Then we will see what happened with floater, prejudice, and inflexible. No prejudice and only inflexible. Then floater and contrarian, no prejudice. Then we can get everything together. So the update equation where I have floater and prejudice, no inflexible, no contrarian for size 4 is written here. This P04 plus 4 P03, 1 minus P0 correspond to a local majority of A in a group of size 4. This corresponds to the tie effect, 2A, 2B. So if opinion A has the benefit of the prejudice here, so it benefits from the tie contribution, it means B does not. It only benefits from local majority. When we solve the fixed point equation, this one and this one, you see here that the two attractors are at 0 at 1, but the tipping point is very low at 23. At opposite, for the B opinion, the tipping point is at 77%, which means that we have a very strong breaking of the democratic balance for A and B, because A opinion, it's enough to start above 23% of support in order to reach majority. While for opinion B, even starting from a huge support like 70%, it will go down below 50%. So it is doomed to lose. So we see that here we have a majority collapse and here I have minority spreading. And the process goes very fast with respect to the update. I consider as an illustration, opinion A in tune with the leading prejudice starting from 25%. After one update, it goes to 26, 2 to 28, 32, 38, 48. After 6 updates, it is already a strong majority at 66%, while it started at 25. So you see that the effect is very strong and surprising. It's important to mention that this tie breaking is independent of the respective global support for A and B, majority or minority. It's applied only locally at 50-50, so it does not seem like a very strong effect that you have to be aware of, because you say, well, this will happen very rarely. But we saw from the number that this is not true. It will have a strong, amazing effect. So this is for group size 4. If I increase the size, then the value of the tipping point, the higher one, will go down, and the number of cycles decreases, so the process gets faster. To show you the effect of the size, I have here an illustration in which I start from A having 45%, but it is in tune with the bias. And I will show you what happened for just one local update. For group of size, here we have 2, 3, 4, 5, I increase the size. You see that up to around 14, up to 14, the size of the group, one update from 45 will still increase the value, which means 45% will reach majority when I will update several times. But for size 2 already, it is huge, 70%. Only one update is enough. This is at 4, it goes already to 60%. This is at 6. So you see that we still, one update will put us up to here above 50%. Here, I will need a second one to move again above 50%. And here I'm just a little bit, so I will need several ones to reach 50%. And here already I go down, which means the tipping point, when I am at 16, 18, 20 size group, the tipping point is for A, but it's below 50%. However, it's above 45%. You see that for the case in which I have an odd size, so it will go down. This is the odd size. So the larger is the group, the more important amplitude, the amplitude of the decrease. So these are for odd sizes. We can understand what happened with the value of K. So this was for K equal 1. So the prejudice go only in favor of A. But if now I want to distribute it among A and B with a probability K, I can have the analytical expression, and then I find that PC is a function of K, and this is the expression here, and we can see how from K value to 1, no, this is from 0 to 1, when it's 0, so the prejudice is against it, so it need to be above 77% to win, otherwise we lose. And the larger K increase, so the more you gain from the benefit, then from 50%, then you will start to have a tipping point which is below 50%, and then you have a huge advantage to win the competition. Of course, we can combine, this was the result for only one group size 4, but I can combine group of any combination which I want. So the equations are much more complicated to solve, but they are solvable and it's possible to write them. So this is an illustration with 20% of single people which will not be in a group for a given update. So they stay with their opinion, but they are not inflexible. They are just stay because they don't discuss it. 30% of group of pairs, 30%, 20% of triplet, 20% of group of size 4, 10% of 5. In this case, if the tipping point, this opinion is in tune or against the prejudice, if it's against the prejudice, PC at 35 is benefit from the prejudice. You see that the tipping point is even lower than only size 4, because now it's at 15%. So it's enough in such a configuration of group for opinion benefiting from the prejudice to start like at 16%. Then it will win the campaign, the debate, the election. Here is an illustration moving from 70% for an opinion which is in dissonance with the prejudice, how it will go down to disappear. And only 4 updates to go below 50%, starting from 70. So it's very strong phenomenon. So the model shows that collective belief and prejudices often take over against initial individual choice. This is why I was questioning the democratic character of the process. This is an illustration where I start from a minority support of 25% against the prejudice, and I will show when I increase little by 10%, the benefit from the prejudice, we will see what happened by having repeated updates. So here, the 20%, 25% will go to 0. Now I have 10% benefit from the prejudice, still it will go down. 20% it goes down. You see, I increase 60% of benefit from the prejudice. So now a majority of people has an unconscious prejudice in tune with this opinion A, but yet is not enough. Starting from 25%, it will lose the election. 70% yet it will lose, even if decrease does not decrease so quickly, but yet the other opinion will win. And yet it has an 80% benefit. So you see, it means that the tipping point in this case is above 25%. Nothing happened. And then all of a sudden, in this case, when you have total benefit from the prejudice, the 25% will make above 50%. So it is the invasion of this minority. This is how the majority would be preserved if you start from a huge support of 75%. In this case, you need to be in tune with spreading. However, this 75% will still decrease if you are in total dissonance, K equals 0 with the prejudice. So you see that's a very strong, amazing phenomenon. Now we move from the other effect, still size 4, and now we have floater, but no prejudice breaking. So we take K equal half. So the prejudice have no effect, but we consider now inflexible, but no contrarian. And then we will see how is what is the update equation and what is the dynamic which is associated to these cases. So I note X is a difference in amplitude in stubborn or inflexible for A and B, and I wrote dk is the departure from 50% of the prejudice, and here we'll take dk equals 0, which means the prejudice are balanced between A and B. the update equation gets much simpler here. It is written here. And now when I want to solve it, it's simpler. It looks simpler, but it's more complicated analytically. But we can get some good result. And I will only show you illustration how it works. We start here from the case where I have x equals 0, which means and a equals 0. This is no inflexible. So I have P1 as function of P. It shows me how I will go by iterating my dynamics. So the tipping point is at 50%. If I start below, you see I will automatically go down. Now, if I increase and I put 8% of inflexible for A, so no one for B, so this is why X is equal to 8% also, decay equal to 0, no effect of prejudice. You see that the difference is that here I had 50% tipping point, 0 and 1 attractor. Now I have an attractor at 0.083. The other ones stay at 1. And the tipping point now has moved back down to 44. Now for opinion A, it's enough to start above 44% to win the debate. If I increase even more to 13% of inflexible, now the change is more drastic because I have the lower attractor moved to 18, but now my tipping point went down to 37. So A need to start above 37% in order to win. But if I increase to 20%, then A will win whatever initial conditions are. So we can have here the evolution. I start below with 0 inflexible, 5% inflexible, 10%, 15, 20%. So you see that in this case, this is an amazing minority spreading. I need to say that indeed, most of the time, you don't differentiate between a stubborn, you can when you discuss with some people, but in the model, you don't need to discriminate between them. They contribute the same way to the local majority. They vote, but they don't follow if they are in minority. However, this element, we have here a kind of interesting and unexpected phenomena. Said that indeed at the critical value xc, which is the difference between A and B, above some critical value of difference, the tipping point and B attractor coalesce and disappear, creating a single attractor dynamics. This is what I was mentioning before. And this value is 15%, which means if I have more inflexible for A or for B, we will see after when I have A and B, of 15%, A is sure to win the debate. This is a case where the difference is less than 50%, 15%. Here, when it is above 15%, so you see that in this case, even if I start from an initial condition here about 20, it's around 28 here, at the beginning, it will be very slow changes, but then I will go up and win. This was only one side inflexible. So of course, in reality, I have two-sided inflexible. So A and B, the difference is not 0. However, the phenomena of coalescence of the tipping point with one of the attractors still occur, but now it can occur on both sides. So it means that X, the difference between proportion of A stubborn and proportion of B stubborn, if it is between XC1 and XC2, I have a tipping point dynamics. So if X is positive, it means the tipping point is below 50%. Below 50% is the advantage of A because it does not need it to have a majority to win. It can start from a minority as long as it is above the tipping point. However, if X is negative, so the tipping point is above 50%, so A will need a majority to keep the majority and win. However, when X is above this XC1, then A will always win. And when it's below 62, A will lose anyway. Indeed, so here I should have here XC2 and XC1 here. This is here a situation of a tipping point where X is in between the two critical values, but we see that the 2% difference in X will yield a drastic break in the democratic balance, because now the tipping point is at 47, so 47.53, so it's a 6% difference, while indeed the difference in stubbornness was only 2%. So 2% give you an advantage of 6%, which is not negligible. This is an illustration of the second scenario when the difference is above the critical value. So I have only one attractor at 74%. So you see I have only 20% stubborn for A and 18 for B. Very small difference, but yet A will be sure to win, even if it will take time. So we will need a long debate or long campaign. This is when X is smaller, so we still have the tipping point with the two attractor at 57. So this is a symmetrical, it's a disadvantage now of A, because it's smaller than the critical value, so it will always lose, even if it starts from a very high value of support. So now let's see, no prejudice effect, no inflexible, what the contrarian do. So the equation here, really now this time it gets simpler and it's easy to solve. And we also, but now it's similar to inflexible, but it's of course symmetrical with respect to A and B, because as I mentioned, the contrarian will oppose the local majority for A or for B. It does not care. Indeed, it's possible to study asymmetric contrarian, and then the situation becomes much more similar to the inflexible effect. And this was done in a recent work with still my colleague from Japan, Taksu Chen. You see here the situation, no inflexible, so I have a balanced democratic system with the tipping point at 50%. If I take 10% of contrarian, so now my two attractor move to 18 and 85%, but still 50% for the tipping point, so it's democratic. However, for 20% of contrarian, I have this interesting outcome that now I will move always to 50%. So this is a way to explain the occurrence of 50-50% election. You can start from a very high difference, like 20 to 80 or even more, 90% against 10%. And if you have 20% contrarian, this will end up at 50-50. So thanks to this universal formula I was mentioning earlier, now it's possible to combine any proportion A, B, C, K and group size. So really it's open a full way to investigate the landscape of the dynamic, which is very interesting and exciting. So at this stage, what can be said? Rather depressing result indeed, because to win a public debate, it seems from this modeling that what is important is not to have good argument, is not to convince a maximum number of agents. What you need is to be in tune with the leading prejudice risen by the issue, to how to position yourself to benefit from the prejudice, to have a maximum number of stubborn agents on your side. So this is not a very exciting prospect to say you want to have your supporter to be stubborn and to make contrarian active on the other side and try to reduce it on your side. So just few illustrations now of prediction and how I've been using the model I use it in the case of issue connected to the European Union. And then, as most of the activated prejudice during a campaign about an issue connected to the EU will be tuned with rejection, even starting from a massive support from European Union, a debate, if long enough, will end up choosing rejection. In my paper of 2004, I made this general prediction in which I say that applying our result to the European Union lead to the conclusion that it will be rather misleading to initiate larger public debate in most of the involved countries. Indeed, even starting from a huge initial majority of people in favor of the European Union, an open and free debate would lead to the creation of a huge majority hostile to the European Union. This provides a strong ground to legitimate the ongoing reluctance of most European governments to hold referendum on associated issue. But some has been tempted by referendum, like in France in 2005, and polls were giving a very high percentage in favor of the yes, but the model and my study, I predicted the victory of the no in a paper of Le Monde. And I predict, it seemed like crazy. How could I make such a prediction when the support for the yes was so high? But indeed, the no did win. And it's the same for the Brexit. When the British, the government decided to hold this referendum, they had a very strong support to no to the Brexit. But finally, of course, the Brexit did win. People afterwards said that this was triggered by the issue of immigration. According to my modeling, no, the Brexit would also have won the referendum at another time with another issue, because this is not which issue is the effect of the prejudice of what was before is much better, when you don't have argument to decide. Contrarian effect on the 50-50 election, this creates a phase transition when you have enough, like around 20% of contrarian. So we have a clear-cut majority-minority phase in which there is a winner into a 50-50 balance with no majority. This creates a so-called hung election scenario. And I started from this approach for the famous 537 ballot in Bush-Gore election in the US, in Florida. So then from this, I predicted that if the model and the explanation is valid, we are going to have now a series of 50-50 election in the coming year. And indeed, this has happened later in Taiwan, in Germany, in Italy, in Czech Republic, in Mexico. Now, the Trump illustration, I see my time is running, so I try to go a little maybe.
7 minutes. 7 minutes.
Okay. So how I predicted Trump victory in 2016, where everyone, including myself, could not believe that this guy will win the election. But indeed, it was a question that he was able to act on the active prejudice by changing them. And at the beginning, the active prejudice was against him. And this is an illustration how, like with a support of 24%, you will go down if the prejudice is against you. But if you benefit from it, you see that 24%, you will win. So actually, Trump, by his shocking repeatedly, he found a martingale to modify the activated prejudice as it benefit. Only him could do it, not Clinton. This is why he won. However, for the last election, then Trump's shocking statement did not shock any longer anyone. People get used to it. But then the modeling was showing that Biden and Trump were competing on the same ground, which was the prejudice of fear. Everyone was fearing the other one candidate, and strong polarization. You had millions of people which are adamantly against Trump and millions of people which are adamantly in favor of Trump. So the competing effect could bring the outcome at the edge around 50-50 in sufficient swing state to make the winner. And then from the modeling, I find that tiny excesses of inflexible or in prejudice will make the winner. My rough estimate were giving a light advantage to Trump, leading to predict his 2020 victory. I was wrong, since Biden won the presidency. But it's important, I have no time here to prove it, to show you, that indeed Biden's victory was very tight, only in a few states with very small number of votes, which made the difference, while polls and pundit was making a massive, predicting a massive Biden victory. So this is why my conclusion was to say, and this is in this paper, actually, I discuss the result and the outcome and the error in my prediction, that the model has been right, but it was my estimate of these advantages which was wrong. So to end up a statement, it's important to state that sociophysics is not a work in progress, it is a field in progress. So a lot of work has been done, much more has to be done to make solid ground of our modeling. And just for the student which will be interested, I really recommend that you have the chance to have a very active group in Poland, which is very creative, very dynamic at Wrocław University. So really, this is a good spot and very nice place. I have been there to go. So I can encourage you to maybe go there to do PhD or to study if you are interested in this field. These are references, there are a lot, and I will advise you my book. It's already now almost 10 years, but it's still very actual. And it's an unusual book with a lot of cartoon and step-by-step, very progressive guidance to explain how it works. The book is still rather expensive. However, you can get it for free in an e-book from your library. Normal, all physics library have possibility from Springer to get this. So I advise you at least to have a look, and you will enjoy it, I guess. So my conclusion is that the issues at stake are huge for our future, which are connected to this dynamics of public opinion. And discovering the law which govern our collective behavior, it's also a lot of fun because we are really at the beginning of a field. A lot has to be discovered. So join the adventure. And thank you for listening to me.
Thank you very much, Professor, for this very insightful talk. And I see that we have some questions from the audience. So a first one would be from, I think, the very interesting question from Jakub Pawłowski. Is it possible to infer something about the real-world timescales of these debates from the number of steps in the calculation? So I think that it refers to the updating procedures that when agents are.
Yes. This is okay. Yeah, this is a very important question to apply the model, of course. Here I am studying the dynamic from one update to another update. But now, in reality, of course, we need to scale this update with real time. In order to do it, what I have been doing, but this is a hand-waving element, is by using polls when to see some difference in the evolution in polls and trying to tune it to an update. So in the beginning of a campaign, usually what I found is that an update will correspond to 2 weeks time duration. However, when we get very close to the voting, so it can be few days. But this is the element which will need much more technical work to do, and also important means and computer and polls, which I don't have. But it will not change all the principle, but it will be to say, will the debate last long enough to go above or below the 50% threshold to win or to lose? So this is a way for the moment, I found to scale it in connection to reality by using poles.
Okay, thank you. Now we have another question. Does any government currently utilize methodology of sociophysics? With risks you've mentioned, do you think some steps should be taken to limit its usage? Or is it proliferation is unavoidable?
I think this is a very important element, and I discuss it in my book, An Ethical Problem. My first answer, and think a fact to look at it is, today politicians have a kind of intuitive way to use this mechanism, but not in a total control. But like when Trump was doing this shocking statement and playing with this reversing of this hierarchy to benefit from it, I don't think he had an equation. However, by discovering what is going on, by having equation, then this opens also a way to oppose it. Now, in order to oppose it, of course, it means that here we really need a total proliferation, which means we need everyone to know the modeling, if of course this is true. And then we will be able to avoid this effect because every side will try to use it. So maybe we can reach against a balance at 50-50 for the attractor or the tipping point. So my point for this is that always to have the knowledge of what's going on has been most of the time at benefit of more freedom, while ignorance was always at the benefit of more power or more totalitarian system. But of course, I don't know. But I am an optimistic about this, and I think that to know what's going on will open much path to more freedom and more fight, democratic fight. Okay, and the last, I have some questions myself. So do you think that there could be some interesting results when we would implement this model on, for example, random graphs, so added some richer structure to it? Because currently it corresponds to the case of a complete graph, right? Yes, I totally agree, and this will something very important to do because when we will do that, that means only doing that will allow to take into account also the heterogeneous distribution of this element. Like you will have area or structure or subspace in which you will have more inflexible, let's say, for A and B, and other part what is the opposite. So really, in order to have a more strong in-depth analysis, we need to do that. But I did not do that, and I hope some physicists will now at some point will do it to see how this will affect the prediction capacity. But this is really connected also to an application in more in-depth to situation. I think in France, I know in France, but I think also like in Poland, you have areas which are more conservative than other urban areas are different. So indeed, we should be able to put in the equation the weight of all these networks which coexist and are different and can have some effect on that. So this will be a very great contribution to the work, yes, but I did not do it. So thank you very much. And once again, thank you very much for your presentation. And that is the end of the day 3 of the Kumquat Conference. We are very honored to have you as our guest. And to the audience and to the people who watch us on stream, I recommend to tune in tomorrow for another session of theoretical physics and another set of keynote speakers. Thank you very much. Thank you for giving me this possibility to explain my work, and good luck.
Thank you very much.